Hello. Today we start a new chapter, a new part of this course, actually the third part of the course. And with the new subject, I've got a new painting here. This is a watercolor by an Arizona artist, Steve Stento. This is called Sun-Kissed Cafe. And by the way, the previous one was with the winter scene, was done by my mother, Fan Swift. All right. In any case, let me talk a little bit about the course as a whole. In the first part, part one, we talked about a single first order ODE. Here's an example, dy dt is t squared times y. So I'm looking for an unknown function y of t. All right, and then second part was second order or higher ODEs, mostly linear, like this one, y double prime, so it's second order, plus 3y prime plus y equals sine of t. So this is a non-homogeneous second order linear ODE with constant coefficients. And now what we're going to be talking about is systems of two or more first order ODEs. Here's an example. We sometimes use this bracket to group the equations together. So we have two unknown functions, y1 of t and y2 of t. And the y1 of t is 3y1 minus t squared y2. And dy2 dt is y1 minus y2 plus sine of t. So this is the kind of thing we'll be studying in this third part. All right, so today I'm mainly going to be talking about matrix operations. Okay, so first, what is a matrix? So something like this, 3, 2, 1, 5, 7, 8 is a 2 by 3 matrix. So 2 rows and 3 columns. I used to have a little bit of a problem with figuring out which is a row and which is a column, but it's pretty clear, right? If you think about architecture, this is it's really a bad picture of a column. Like a column in a building is this big pole that holds up the building, okay? All right, and then which is, first you do the number of rows, and the second the number of columns. And as I see here, I'm not sure whether you have 1 L or 2 in columns. It does matter, but in the math course, I guess we're not going to take points off if you spell columns incorrectly. All right. So the 2 by 3, by the way, which comes first? I remember RC stands for Roman Catholic, and I'm not Roman Catholic, but I'm pretty close. Even years ago, I came up with this little mnemonic for like if you have a 2 by 3 matrix, which is the rows and which is the columns. All right. Okay. So this is the 2 by 3 matrix. Okay. So what are the operations? The operations are scalar multiplication, addition and subtraction, and matrix multiplication. Okay. So scalar multiplication is possibly the simplest one, and it can work for any matrix. Okay? If I got a 2 by 3 matrix like that, I can say, I don't know, let's say 2 times that. A scalar, or 2, times this 2 by 3 matrix is going to be another 2 by 3 matrix. It's going to be 6, 4, 2, 10, 14, 16, right? Okay, so that one is fairly straightforward. Okay. Now addition and subtraction. To add or subtract two matrices, they both have to be exactly the same size. So I can take this one here, and I can add that first one to the second one. They're both the same size. So I can add it, and I get, oh, it's starting to get hard, 9, 6, 3, 15, 21, 24. So if I have a 2 by 3 matrix, and I add another 2 by 3 matrix, I get the result is a 2 by 3 matrix. Okay. Now, matrix multiplication is maybe the trickiest of these. All right, I'm going to give you an example of matrix multiplication. Let's just do this example. Say 2, 3, 4, 5, 6, 7. Okay, this is an example of matrix multiplication. So I get 2 times 6 is 12, plus 21. And here I get 24 plus 35. Okay, and what I did, and in order for me to do matrix multiplication, I almost always have to write them down in the order that they are and use my fingers, right? I do that times that plus that times that. That's the first component. That times that plus that times that. That's the second. And what I often like to do is, at least for me, you can find out what works for you. I like to do the multiplication, okay, in my head, and then write down the result. But don't try to do the multiplication and the addition in the same step. So the result would be 12, this is what, 33 and 59. Okay. So let's think about how this worked a little bit as far as the size. This is a 2 by 2 matrix. This is a 2 by 1. It has 2 rows and 1 column. This is often called a column vector, okay? And this works because these two inner numbers are the same, right? Then I can, these matrices can be multiplied. They're comfortable for multiplication. And the result is the outer number. The result is a 2 by 1. This is a 2 by 1 matrix. Okay? Just as an example, if I had, say, A, B, if this was a 7 by 9 matrix, and this was a 9 by 3 matrix, the result would be AB, which is, those are equal. So the result is a 7 by 3 matrix. Okay? That's really important for some of the web work problems. All right. So let me show you a little bit more symbolically, rather than just this example, how matrix multiplication works. So one of the most common examples with matrix multiplication is multiplying 2 square matrices of the same size. So let's in fact do these 2 matrices, okay? Now, can I multiply them together? Yes, this is a 2 by 2. This is a 2 by 2. Those are equal. So the result is going to be a 2 by 2. And what is it? Well, I do that times that plus that times that. So I get 2a plus 3c. That's in the upper left entry of the result. Then upper right, I get 2b plus 3d. And then I have 4a plus 5c. And then I have 4b plus 5d. Okay, this result is a 2 by 2 matrix. And I've written this out so you can kind of see a little bit of the pattern. You notice that on the right, there's 2, 3, 4, 5 over there. And here we have a 2, 3, 4, 5. It's just like that pattern. Now, I have an A there, and an A there, and a C there, and a C there, B, B, D, D. I know. It has sort of a nice pattern. But I do it all with my fingers. Let's do an example. If it wasn't B and D, but let's just put in some numbers. Let's put in some negatives in there now. Let's suppose I have this times -1, 0, 5, -2. All right. So what I'm going to do here is do the addition and take care of the sign in my head, but not try to do the addition as well. The sign and the multiplication in my head. So I get -2 plus 15. Okay, that's that times that. Plus, over here, I get 2 times 0, which I can leave out, -6. And then I get this bottom left, I get 4 times -1, -4, plus 25. Then I get 0, which I left to right, -10. So the result is 13, -6, 21, -10. Okay. All right. Let's do another example. Say 2. I guess I haven't done this one yet. 2, 3, 4, 5, and for general, let's leave the A and B as variables, not as numbers. Okay. So let's see, does this work? This is a 2 by 1. So I know it isn't. It's a 2 by 2 matrix. This is a 2 by 1. Again, these are equal. We've done this kind of example before. Those are equal, so the result is a 2 by 1. It's going to be 2a plus 3b. That's the first entry, and then I have 4a plus 5b. That's the second entry. Okay. There's another way of thinking about this, which is useful. Okay. Okay, I can think of this special case of a square matrix times a column vector. Whereas the way it works is I take a linear combination of the columns of that square matrix, right? So this matrix multiplication is that first column times A, plus the second column times B. Okay, that's a nice way of thinking about it. And while we're at it, let me just mention an example of matrix multiplication that doesn't work because the sizes of the matrices are wrong. Could I do this? Could I do 3, 4 times 5, 6, 7, 8? Is that defined? Think about it. Is that defined? Well, how do we tell that? This is a 2 by 1 matrix. This is a 2 by 2 matrix. These are not equal, right? 1 is not the 2. So this is not defined. Okay? When you put them next together, when you put them next to each other, those two inner numbers aren't the same, so this matrix multiplication isn't defined. And this is an extreme example of the fact that if I multiply two matrices, A times B, that's not equal to B times A in general for matrices A and B. Even if they're both defined, in order to be both defined, they have to be square. But there are examples of square matrices, A and B, both of the same size. So AB is defined and BA is defined, where AB is not equal to BA. It's probably worthwhile to do an example like that. I do 1, 2, 3. No, let's not do 1, 2. Let's make it 0. Okay. What is this? Okay. Ooh, that's 1 plus 0. Okay, 4 plus 2. Using my rule, I do the multiplications, not additions. That's going to be 0 plus 0. That's going to be 0 plus 1. Okay. But what if I take it in the other order? 1, 4, 0, 1 times 1, 2, 0, 1. Then I get a 1, and I get a 2 plus 4, and I get a 0 plus 1. Wait, on the bottom left, 0 plus 0, and I get a 0 plus 1. Oh, look at this. For this example, if that's A and that's B, this is AB and this is BA. Okay? And AB equals BA. Okay? So did I lie to you? This word in general, okay? In general, AB is different from BA. But I've chosen an example where AB equals BA. Don't forget that from a logical point of view, this allows the possibility that they're equal. So maybe I should do an example with when they're different. Hopefully I can come up with one. Suppose that A is, let's just say 1, 1, 1, 1, and B is 1, 0, 0, 2. What is AB? 1, 1, 1, 1, 1, 0, 0, 2. All right, so I get 1 plus 0, 0 plus 2. I get 1 plus 0 and 0 plus 2. Okay, what about BA? Okay, BA is 1 plus 0, 1 plus 0, 0 plus 2, 0 plus 2. So in this case, we do have an example where AB is not equal to BA. And now I can actually stop. It's true that AB isn't BA in general because I found one counterexample to AB equals BA, right? There's one case where they're different, okay? So I've proved this fact, right? If I wanted to prove the fact that something was equal, I would have to try every single possible matrix there'd be. But to show that they're not equal, we just have this counterexample is good, okay? And then, of course, there's also times when maybe AB is defined, but BA isn't. We've done that example. That's a 2 by 2. That's a 2 by 1. That's defined. That's not. So, of course, it can't be equal. All right. So I know this is probably getting kind of long, but hopefully this is review. And if it's not review, you've got some work to do. You got to go check out Khan Academy or something. The book has a short introduction to matrices. Paul's Notes does, but hopefully you learned about this in high school or somewhere. But let's go and talk about how you would use it in this case. Okay, so let's take this problem, and this is very much like, I think, Weber problem 4. This system can be written in terms of vectors and matrices, okay? So I can think about these two equations as the equality of one vector with another, okay? There's two equal signs. I can write this with a single equal sign, right? I can write this as dy1 dt is the first component, and dy2 dt is the second component of this 2 by 1 matrix, right? And that is equal to 3y1 minus t squared y2, and that is y1 minus y2 plus sine of t. Okay, and here's a 2 by 1 matrix. Okay, so there's only one equal sign here because it's a quality of vectors, which means that the first component's got to be equal, bingo, and the second component's got to be equal, bingo. Okay? Now, we've been talking about matrices and vectors. This can be written as, I'll just do the example, 3 minus t squared y1, 1 minus 1. I think of the coefficients the coefficient in front of y1 is 3. The coefficient in front of y2 is minus t squared. I'm not done, by the way. Maybe I should add it now before I do the multiplication. Plus 0 sine of t. All right? So here we've got this 2 by 1 matrix and a 2 by 2 matrix, a 2 by 1 matrix or column vector, and here's a 2 by 1 column vector. I can multiply these two together because the 2's are equal and get a 2 by 1. And I can add a 2 by 1 to a 2 by 1 and get a 2 by 1. Now let's think about the numbers, right? The 3 is the thing that multiplies the y1 minus t squared, thing that multiplies the y2 in this first equation. And here I have a 1 times y1 plus negative 1 times y2. And then the parts that don't have any y's in it at all, there's the 0 and this thing. Okay? So this thing here you get rid of this too. what I showed is another way of writing this thing here is I can say let the vector y be y1 in y2. Okay? And that's actually a vector function. What I really mean is that y of t is a vector y1 of t, y2 of t. So I got a vector valued function. The input is a number t, the output is a vector y vector of t. So I can write this whole thing as d dt of y, all right? This thing here, the derivative of the vector is the derivative of the first component and the derivative of the second component. It's the two components of dy dt. All right? And then that is equal to 3 minus t squared, 1 minus 1 y, plus 0 sine of t. So we have two different ways of writing the same system of two first ordinary differential equations. Okay? Here it's written as two equations, and here it's written as a single vector equation. Okay? All right. And so one of your problems in the web work is very much like this. You've got to identify this matrix in the front of y and this vector that doesn't have any y's in it. This can have t's in it. This can have t's in it.